Swayam Prabha. Digital India. Educated India.
Okay, so today we will kind of dig deeper into 2D line shapes. I'll show you some actual experimental data and try to kind of identify features, try to learn how to read 2D spectra in general and see what we can learn from that. Before doing that, let's take the situation, a scenario where you have this kind of coupled oscillator kind of system, kind of what we have already spoken about. Let's say there are two excited states. In this case, they're coupled, so they share a common ground state. If they're not coupled, they will not share a common ground state. For the sake of convenience, I'm labeling them 1, 0 and 0, 1. Don't confuse them with the vibronic structure we spoke last time. They're simply saying 1, 0 is excited state on the left oscillator, 0, 1 is excited state on the right oscillator. Now, usually when I have two quantum states coupling together, I could have self and cross interactions of the one quantum states to create a manifold of two quantum states. Okay, so this kind of, you can have all kinds of higher line quanta. And here, if I take just one oscillator, I'll have its associated two quantum state. The other oscillator will have its own two quantum state, and if they are really coupled, then you will have some kind of mixed state, right? Mixed two quantum state. Think of excitons, for example. If there are two excitons, two kinds of excitons in the system. Excitons of one kind can form what we call as biexcitons of one kind. You'll have two excitons coming together form biexcitons of other kind. But excitons of one kind, the other kind can come together to form a mixed state. In fact, sometime in this class, I'm going to show real experimental data of exactly this scenario where we have this kind of mixed two quantum correlations. So anyway, going back, we have these picture. Okay. Now again, going back to pump probe, we always nice to think of pump probe, right? When you think of pump probe, let's say I have a situation where I am exciting only the photoexciting exclusively the oscillator on the right. Okay, so excite oscillator on the right. What would be the contribution overall to my pump probe signal? You'll have the ground state bleach associated with that oscillator, right? So you'll have a bleach, which I will label 2 here, associated with that transition. Okay. You'll have the excited state absorption. You'll have two excited state absorption bands because you're populating the state here. You'll have one to the two quantum state associated with that oscillator and your mixed two quantum state, right? Two excited state absorption. But because you're depleting the ground state, you will also see a ground state bleach the transition of the other. You'll have 4 features. Agreed? Is everybody fine with that? 4 features. In fact, that's what we see here. 2 ground state bleaches and 2 excited state absorption. Now, typically, in most of the systems, your 2 quantum state, because of what we call as anharmonicity, is slightly lower than the twice the 1 quantum energy. Which means my 1 quantum to 2 quantum transition, 1 quantum to 2 quantum transition energy will be slightly lower than the 0 to 1 quantum transition. That's because of binding, attractive binding. Okay. So anharmonic coupling can change. So if there is no anharmonicity in the system, which means that think of again in terms of excitons come together, there is no interaction. In principle, you form a 2 quantum state, but the 2 quantum state is exactly twice the energy of 1 quantum state, no anharmonicity, right? But if I have some kind of attractive interaction, 2 excitons come, they kind of bind together, the binding will result in stabilization of what we call as a 2 quantum biexciton state, then the bi-exciton will have certain binding. So the 2 quantum state energy is slightly lower than the twice the 1 quantum energy. So in that case, this energy difference from 0, 1 to 0, 2 will be slightly lower compared to 0 to the first excited state. So accordingly, your excited state absorption will be slightly at lower energy compared to your ground state breach. Okay. If you have no unharmonicity, these two will overlap, one on top of each other, and sometimes they kill. So it can happen that you don't see any ground state bleach. It's because the ground state bleach overlaps exactly with an excited state absorption to a 2 quantum state which has no anharmonic coupling. Then I'm sorry, you're in a very bad situation. You don't see any signal, and you'll be scratching your head why you don't have a signal. It's because you have a system which has no anharmonics, which will never happen because anharmonic interactions are ubiquitous. It's kind of there, given to you. Okay, so that's when you're exciting your right side oscillator. Let's say you come with slightly higher energy and you excite your left side oscillator. Here you will see now the bleach associated with this guy, 2 excited state absorption bands, and of course the bleach of this. Now here I'm not plotting the exact energetics, but it's not inconceivable in a situation where the pump probe spectra will look identical. But the thing is, you will see a band here, for example. In this case, this corresponds to a transition from 0, 1 to 1, 1. In this case, it's transition from 1, 0 to 2, 0. Completely 2 different transitions, but the spectral signature is exactly the same. There is no way to distinguish one from the other. Right? The same here. You can see a transition here. This is 0, 1 to 0, 2, and in the other case is 1, 0 to 1, 1. And there is no way to distinguish one from the other. Okay, and that's the problem of pump probe spectroscopy. And we will now see how we can overcome this by using 2D spectra. So let's do an exercise. Okay, let's do an exercise. All of you take your pen and paper. Let's take this seemingly complicated landscape and write down for rephasing. Remember, rephasing is minus K1 plus K2 plus K3. So you start from the bra side, ket side, and then the last one also is either bra or ket, but you should make it plus K3. For rephasing condition, for this situation, write down as many double-sided Feynman diagrams as possible. Sorry, so I'm saying for this particular structure, when you have this particular electronic structure, electronic states, write down all possible double-sided Feynman diagrams for the rephasing condition. All right. How many Feynman pathways, Liouville pathways, not Feynman pathways, Feynman diagrams, Liouville pathways were you able to write? You can just shout out 4, okay? Even if it's 0, you can say 0. 20, also 20. Okay, so let's say I'm going to show you all the pathways, and then you can tell me how many of those pathways lie in your pathways. Okay, so there are 8 pathways, right? Have a look at the pathways for now, at the diagrams. How many of you got at least one of them? Not even one? You got one. Okay, you got one. Anybody else got at least one? No? You got the first one? Okay, that's good. You got 2. Okay, it's going to increase. Now, who is next? Okay, like, anybody else got 2 at least? Nobody to beat Sudarshan here? Okay, let's kind of understand why you haven't got even one possibly. So the idea is always you write your states, you have all possible states, right? And you're writing this projection. So whenever you have an arrow going in, you need to have an excitation, right? In whichever direction you're going. If an arrow is going out, you should have the excitation. Now take the first diagram, okay? It's minus K1 plus K2 plus K3, okay? So it's minus K1 plus K2 plus K3. So it's consistent, right? It's consistent with uh, the conditions. So I'm starting with 0, 0. So it should be 0, 0, not just 0 here. Doesn't matter. 0, 0. I come from this side, so I have to raise this part. I'm raising this part from 0 to 0, 1. I'm creating this coherence, right? I'm creating this coherence. Then I come with my second pulse, right, plus K2, and I'm taking this 0 up to 0, 1. So my first and second pulses are generating at the end. What is this? It's a population, right? It's a population. And then the third pulse is going to come this side. It's going to de-excite. Arrow is coming out. It's de-excite. So where will it de-excite? Back to ground state. So 0, 1 becomes 0. What is this? This is a coherence. Coherence oscillating at what energy or what frequency? The frequency difference between this, right? So your excitation here is creating a coherence. The first pulse is creating a coherence, which is oscillating at this frequency. And your final excitation is also creating a coherence, which is oscillating at the same frequency. Everybody with me on that? Everybody with me on that? And it is going through a population term. Okay? So, of course, there will be identical diagram for both the right oscillator as well as the left oscillator. These are the two diagrams. Okay? In pump probe, if I have something like this, what does this correspond to? What kind of feature does it correspond to? There are only two features, right? In pump probe that you need to worry about. Ground state bleach. It is going through a population term, if you want to think about it. You can also think about, I'm exciting a 0, 0, 0, 1 coherence, and I'm detecting a 0, 1 coherence. So in a 2D spectrum, if you think about it, your 2D spectrum is the spectrum between excitation energy and emission energy. Excitation energy depends on the frequency of this coherence, right? That's what one of those axis of your 2D spectra is. Emission energy is the energy at which the emission, nonlinear polarization, is emitting, and that is emitting here, right? So in a 2D spectrum of omega 1 and omega 3, where would this pathway appear? Along the diagonal. You excite at the energy of omega 0, 1. You emit at the energy of omega 0, 1. Same energy. Make sense? I'll show you data, but visualize this. So these two features, which corresponds to ground state bleaching, which we all agree on, is going to appear along the diagonal because it's absorbing at the same energy as the emission, or the emission energy will be at the same energy as an absorption. Does anybody think it's complete nonsense? Okay, that's always good. You may not understand, but if you think it's complete nonsense, then I'll repeat everything. That's fine. All right, so these two, we are good. Now, what is the other feature that appears in your pump probe along with ground state bleach? Photo-induced absorption. Photo-induced absorption is basically you create a population and then you have an excited state transition. So, for any kind of, and even in refacing 2D spectra, you need to have excited state absorption features. Kind of makes sense because you're creating population. So, here as well, same. The first two interactions are exactly same as here. You go here, but I can move this interaction now onto this direction, still keeping plus K3 condition, phase matching condition. I move it here. So I'm exciting from my ket direction. So 0, 1 becomes 0, 2. So I'm exciting, or excitation leads to a frequency polarization at 0, 1 frequency, but the emission will be at the 0, 2. Right? Actually, I made a mistake here. I made a mistake here. This has to be 0, 1. It has to be 0, 1. I'm sorry. It's kind of mistake everywhere. I'm so sorry. I just copied it. Oh, here it will be 1, 0. Agreed. I'm making too many mistakes. Thanks for catching. You agree, you're right. But you get the point, right? I'll probably update it when I'm posting this on the notes. Okay, so I'll have an excited state absorption, very good. And here, of course, there are two additional diagrams because I have excited state absorption from 0, 1 to 1, 1, the mixed state, as well as 1, 0 to 1, 1, the mixed state. So you have 4 excited state absorption, right? So all the excited state absorption will have absorption to one state, and the second one will be emitting at slightly lower energy. Because remember, by definition, my 1 quantum, 2 quantum transition will be slightly at lower frequency, right? Okay, good. So that's excited state absorption, ground state bleach. Something I will have now, which I didn't have earlier. Are these two diagrams. So here, if you look carefully, you're coming with one excitation. I go to 0, 1, the same ground state. So if I come from this direction, I can go to 1, 0. What is this? This is a coherence between these two states. It's a coherence between these two states. It's not a population. So I said two-field interaction always leads to population. In this case, it's actually generating a coherence. We kind of saw a similar scenario in the last class when you're talking about impulsive vibrational spectroscopy, right? But it's the same thing here. And of course, it will emit. So what you will see here is that I'm starting at the frequency of 0, 1. I'm starting at the frequency of 0, 1. And I'm emitting at the frequency of 1, 0. Right? Here is 0, 0, 1. Here 1, 0, 0. 1, 0 is this energy, 0, 1 is this energy. Which means I'm going to see a signal which is off diagonal. Right? And this off diagonal simply is off diagonal features exactly along the off diagonal condition corresponds to presence of coherence between excited states, right? They are indicative of cross coupling, coherent coupling. Okay, make sense? Okay, let's look at real experimental data. Oh my God, I didn't have the reference here. So this is a physical review letters from Andrei Tokmakov group, I think in Chicago. I think this is probably the first 2D spectra ever recorded. I mean, I may be wrong here, but it's really a seminal work. And it's 2D IR. And 2D IR, what they do is that they take this particular molecule, and this molecule has two carbonyl groups. My chemistry is bad. I hope this is carbonyl. C double triple bond O is carbonyl, I think. Okay, and these are two oscillators. It so happens, depending on, because of the molecular conformations, these two have slightly two different frequencies. Slightly two different frequencies because of how they are. They're not symmetric. But because they're kind of tagged along with, by the way, it's about vibrational mode, vibrational frequency. We're talking about vibrations of this. Is C triple bond O vibration. They'll have two different frequencies. And because they're kind of coupled to the same molecule, they're kind of having a common ground state. Okay, so and there's been kind of a very kind of fruit fly system to do 2D IR. The 2D IR because it's all done in the infrared. And what you see here are bunch of features. Okay, this is a refacing spectrum, by the way. This is omega 1, your excitation energy, omega 3, your emission energy, and because we are looking at a chemist's paper, it's all in wave numbers. If physicists have done this, it will all be in EV. So it's kind of different kind of nomenclature used by different groups. Sometimes people also put wavelength if it is dumb spectroscopists like me. I should delete that from recording. It should not be recorded. All right, so if you look at the features, by the way, to be really precise, this is the real part of the refacing spectrum. So remember, there's a phase information when you measure the signal. which means you have access to both real as well as the imaginary part of your nonlinear response function. Okay, later on I'll show you how they are going to look like, but for now don't worry. And you will see there are two features right on the diagonal. That line there is a diagonal, which is mean that it's absorbing and emitting at the same energy. Absorbing and emitting at the same energy. These two correspond to ground state bleach, which are the first two diagrams. Everybody happy with it? Note of caution, don't confuse this emission to photoluminescence. It's not. It's emission associated with the third order nonlinear polarization. Right? That's the emission. It's not emission that you're used to. So it's very easy to say, what is this emitting here? I know photoluminescence, there is always a Stokes shift. I cannot absorb and emit at the same energy. We're not talking about photoluminescence. We're talking about emission of the nonlinear polarization. Your first absorption is the first field generating the coherence. The first field generating the coherence, and then the third field generating again a coherence, and you're correlating those two frequencies between the first and the final interaction. Okay? Everybody is fine? No confusion there? Okay, so we have diagonal features, and these two diagrams corresponds to coherence between the states. And here you absorb at 0, 1, or you excite the 0, 1 coherence and emit the 1, 0 coherence. Those are these cross peaks right off the diagonal. Right off the diagonal. Right? Which absorbs, excites here, but emits at the higher energy. This absorbs here, but emits at lower energy. Absorbs here and emits at lower energy. Okay? Everybody happy with that? Everybody happy with that? Now look at excited state absorption. Remember these two states, of course, we all know the mistake in this. It should be, you know what these mistake I made. Pardon me for that. So let's say you're forgiven me for this mistake. Just look beyond my mistake. These two states, basically, you're absorbing at 0, 1 and you're emitting at 0, 2, 0, 1 coherence. So it'll be slightly lower. In fact, you have two features here which are slightly below the diagonal. Slightly below the diagonal. Right? So those are my excited state absorption corresponding to excitation to two quantum spectra with so-called self-correlation. Basically, two quantum associated with each of those bonds, independent, not coupled. It's not 0, as I said, I made a mistake, it has to be 0, 1. So it's the energy of difference between 0, 2 and 0, 1. So this transition energy, which will be slightly lower compared to this. So I'll absorb here and emit at this energy, which is slightly lower. So it will be slightly below diagonal. Make sense? Similar to in pump probe when we did bleach and excited state absorption at lower energy. And you have two features here. Okay? Excited state absorption. Remember, you have two more excited state absorption features associated transition from 0, 1 or 1, 0 to your 1, 1 state, the mixed state, and those are these little guys. Okay? So in this one experimental spectrum, it's kind of spectacularly pedagogical to kind of understand and assign different features that you can observe. Kind of very, very remarkable. Right? Something to note here, which I'm not going to discuss a lot more, but kind of something to note, is that if you look at the diagonal features, there is very symmetric line shape. Very symmetric along the diagonal. Okay? And if you look at the imaginary part, this is what is called absorptive line shape. It's like a very nice Lorentzian, nice absorption. Okay, it goes like that. And if you look at the imaginary part, which I'm not going to show you here, it's going to look dispersive. There is a very specific phase which is imposed on the system because of the imposed on the optical response because of the system. and it's normal to find this exact phase shift. It so happens this absorptive dispersive behavior, the real is always absorptive, the imaginary is always dispersive. However, of course, when you're trying to do research, you will find things, and we found in one scenario exactly opposite. There was a phase scrambling, and that's because of many body interactions. So many body interactions can scramble phase, okay, which add additional phase basically. We'll not talk about it, just keep in mind. So there is some information encoded also, not just in appearance of features along the disk, along the 2D line shape, but also the specific spectral structure each feature has. Will give you some information about system path interactions, which actually, this spectrum is extremely rich. This is the maximum amount of information one can extract using a nonlinear spectroscopy method. It has all possible information for you right in this one snapshot. So it's kind of very powerful. Okay, all good? Questions? Now I want to kind of focus on our cross peaks here, right? These are my off-diagonal peaks, right? These are these peaks here. Okay. Now that 2D spectrum that I showed you earlier was taken at one particular tau 2 or the second delay, right? You're not changing the delay, right? Now let's think about a situation where you start changing the delay, or you're measuring this 2D spectra at different delays between the population and the last interaction. In other words, you're letting, here is not a population, it's a coherence, but whatever you're generating after two-field interaction, you let it evolve for different times and you measure your 2D spectrum. Okay. Now, if I measure such dynamics of just this cross peak of diagonal features, can anybody kind of guess how the dynamics would look like, how the amplitude of that signal would look like? Would it be an exponential decaying function? It'll be population. It's not a population here. Very good. So what would we get here? Oscillations. A coherence will always oscillate in time. If you let it change the delay between this and this, then you are going to oscillate. It will be a time oscillating. Where will so if I measure this 2D spectra at different population waiting times or different tau 2, I'm going to see oscillations. Only on the off-diagonal features. Only on the off-diagonal features. Going back to what we have learned in the previous class, you saw that phonon spectra in pump probe, right? If I take a 2D spectra, those phonon coherences will appear exclusively on the off-diagonal features. You kind of separate it out. You can kind of see that. That's because the two-field interaction, you are generating a coherence, and coherence by nature will oscillate. This is my T2 or tau 2, whatever, my second. The time delay between my second pulse and my third pulse. Now you will ask what is so important about this? Again, going back, it's a very strong indication of existence of coherence between two states. I'll show you a couple of examples, actually more than a couple, of real experimental data. Okay, ready? Ready for this? Good. So this is something that we have done on this material system, two-dimensional perovskite. I kind of showed you already. It so happens in this perovskite, there are multiple excitons, at least two strong excitons, which are separated by about 35 MeV. This is not a phonon mode, by the way. These are two distinct excitons which are present in the system. We did this experiment. Of course, this line shape is extremely complex for various reasons. But if I just take out this off-diagonal features that I see here, you will see as I change the population time, which is a delay between the second pulse and third pulse, these have oscillations on top. Whereas the other features on the diagonal, so on and so forth, they are just exponentially decaying. And if I take only that oscillation and Fourier transform it, you get a beautiful peak around 35 MeV, which is the energy separation between these two states. So I have two states exactly like before. I'm creating along the off-diagonal feature coherence between these two features. Okay, and then you'll see an oscillation at that frequency. Okay, it defaces extremely fast because of the very strong defacing in these materials, but you see it. The line shape is a lot more complicated. You'll ask me why I don't see anything here and so on and so forth. Know also that 2D spectroscopy with love is sometimes called as bloboscopy. Blobs moving around. That's because you don't get very nice features. You get big blobs moving around. And sometimes these overlapping blobs can make our life complicated. So that is a small complication on top of this. But we do see this oscillation. Now I want to kind of allude to a very important kind of topic where there has been a lot of discussion about quantum biology in photosynthetic systems, light harvesting complexes, where very early works, especially early 2000 to 2010, the first decade of 2000, there has been a lot of work where people have done on this. This is actually a FMO complex, which is also a light harvesting thing in nature, and it's a protein, I think. And people have done these experiments, and they have seen off-diagonal features oscillating. Okay, you can see some small oscillations here, you can see little oscillations here. So there are oscillations, and because of this humongous structure, this is a huge protein structure with a lot of chromophores kind of attached over it. It kind of inspired people to say there is inherently quantum coherence in biological systems. Sort of in a sense, if I have a light harvesting complex with multiple chromophores, I put an excitation here, the excitation is already there because it's quantum coherent. There's a strong quantum correlation between different chromophores, right? And it has been proposed, but over a period of time, people realize these are not really, not necessarily quantum coherence signatures, but vibrational coherences, like we discussed previously. It has nothing to do with correlations between different electronic excited states, but rather just coherence between vibrational state within the single molecule. It's not necessarily coupling. And if you are interested, I strongly suggest you to go and read this extended review called Quantum Biology Revisited. Out of all the big names are here of 2D community, very nicely written, kind of very nice discussion of how 2D spectroscopy probably yielded some information which is not necessarily rightly interpreted, but the data was clean, it was spectacular data, but it was probably not accurately interpreted, and later on it was clarified later. So it's kind of a very nice historical perspective. Okay, so that's about cross peaks. Now I want to go back to, okay, any questions so far? Okay, cool. Okay, I want to go back to our experiment. Remember, we were coming with 3 pulses, and your time ordering was such that this was your refacing spectrum. You're coming with, so in this configuration, you're coming with A pulse, C pulse, and B pulse. Okay, minus K1 plus K2 plus K3. Okay, now let's say I change the time order. I come with my B pulse, then the C pulse, then the A star. What would it look like? Can you write a double-sided Feynman diagram for this? So in this case, you have 2 interactions, both from the ket and then possibly a bra, right? It's plus Ka plus Kc minus Ka. So 2 interactions from the ket and the bra interaction. Can you draw double-sided Feynman diagram for this kind of time ordering, which I've considered, which is different from my rephasing time ordering. Yeah, no, it should take 3 level, like 0, 1 quantum and 2 quantum. It's like previous case. You can just take that. Yeah, you can just consider the previous condition. The one that we have been working with. Anybody find anything interesting after the first 2 interactions? After the first 2 interactions, is there anything interesting happening? So let's say you have the 0 state, 1 quantum state, 2 quantum state. You have 1 interaction. Second interaction also from the same direction. After 2 interactions, what is the kind of density matrix that you are generating? Is it a population? Is it a coherence? Who says it's population? Remember, population is projection of the same state on the other, coherence is projection. Yes. So you're going to generate a coherence between ground state and the 2 quantum state. It's going to look something like that, right? Make sense? Now think of an experiment where I do my experiment, but I vary the time delay between these 2 pulses, my second and third pulses, and use Fourier transform that to create my excitation energy axis. Then you will be correlating my 0 to 2 quantum energy to 1 to 2 quantum energy. Right? These are the 2 possible pathways. So I'm going to access 2 quantum coherences. I'm going to kind of see kind of multi-quantum correlations in this 2Q plot. Okay? So in this case, your excitation energy axis will be twice the 1 quantum energy. I'll show you an example. Is everybody okay with that? If you're a bit confused, I'll show you some experimental data. You will kind of hopefully get the point. So that's experimental data. Don't worry about it. So in this case, again, perovskites. I have 2 excited states, XA and XB, and I can have 2 biexcitons associated with it. Okay, I'm not writing the mixed state yet. 2 biexcitons. Everybody comfortable with that picture? This is not that different from what we have discussed so far. Now I put self interactions, basically these kind of diagrams, where I create coherence between ground and biexciton state and measure exciton. So on one axis, you have the 2 quantum excitation form of the time delay between the second. Previously, you were changing the delay. Here, I'm changing the delay between second and third. That's what interesting is, because if I change the delay, still accessing 1 quantum coherence. A 2 quantum coherence, I want to be able to access that. So I'm second and third pulse, and then Fourier transforming that to generate my excitation axis. Think about how you generate your 2D spectra. Remember, transform of some delay that you are generating, right? Omega 3 is always the final emission energy response function. See a feature here, okay? This thing, you're correlating 2 quantum energy. You're correlating 2 quantum energy and 1 quantum. There is no biexciton binding. My 2 twice the 1 quantum energy. In that scenario, a feature right on the diagonal. The fact that there is a bit of binding, you will see a feature below the diagonal. And the shift exciton binding energy. Now, this is the most accurate way of estimating. You might say, I can measure 1 quantum spectra absorption associated to 1 quantum, 2 quantum excitation. Biexciton binding energy, true. But remember, 1 quantum excitation pathway has so many contributions, very hard to estimate. In fact, if you go into this paper, JChemFIS, we have estimated bi-exciton different methods, and we have noted how using the two the highest precision in the bi-exciton binding because in the data. Okay, so what diagonal, but if I go to the other exciton, it barely only a little shift here. The reason for that is that this exciton has humongous bi-exciton binding energy. This one is almost a harmonic interaction. There is no much bi-exciton binding. It's kind of fascinating to think about it. In addition, you have this additional feature. This is basically, remember there are two pathways. So what I showed you below diagonal is this pathway. You have the other pathway too. So this is other manifestation of multidimensional spectroscopy where you not only correlate one quantum energies like in rephasing or non-rephasing, but you can also correlate one quantum with two quantum energies. Now it's need not stop here. You can go to Chi5, Chi7, Chi9 and explore all possible correlations. It's not impossible. It's not inconceivable. It will be just extremely painful. Although there are some emerging methods which may allow us to access them with reasonably good ease. Okay, which are on Monday I'm going to talk about experimental methods. So there we can discuss. Come again? No, it is. It's the way the 2D plot is. The diagonal is this. It's basically 2x line. It's the way, because we plot it a bit beyond, it looks like that. It's not a pretty nice looking thing, but it is a diagonal. Okay. By the way, because you have also the mixed bi-exciton state, you also get additional features. I'm not going to talk about that. You can create this kind of coherences here. So this is our experiment and this is our simulation. We can reproduce the experiment almost perfectly, which is kind of beautiful. Okay? Make sense? Make sense?